No, you don't confuse it. Everyone knows like LP spaces.
I honestly, I don't know what's horrible.
You open curly brackets inside section name. Like this, and then type whatever you need to.
What does it break in yours? What is it?
Oh, that's the funny German O.
The O with the dots.
Oh, the amount.
Wait, it's got a name?
Yeah.
Is it well?
Yes.
The two dots. Is it?
Yep. What do you call the hat?
Circumflex.
It's all the diacritical marks, isn't it?
Critical.
Like the other day when I was doing some Romanian stuff, what all these little symbols mean.
Romanian. Cool.
Well, they've got 30 alphabet letters or something like that.
Oh, there's a double dot.
Okay, good afternoon. Welcome to measure theory. So today we're going to discuss one of the exercises again, but since last time we stopped just in the middle of a proof, I just want to finish the proof before we start with the exercises. So last time we started proving that every Riemann integrable function is Lebesgue integrable and the integrals are the same. And I'm not going to write all the formulas down that we had last time. Instead, I just drew a picture that summarizes everything nicely, I think. So we have, we start with the function f, which is Riemann integrable. And then we looked at these upper sums and upper Riemann sums and lower Riemann sums. We started proving this theorem by constructing, by taking this subdivision of the interval and constructing simple functions, phi n and psi n. So phi n corresponds to this lower Riemann sum, so it's always below f. Psi n corresponded to the upper Riemann sum, and it's always above f. So this is basically summarizes everything we've done last time. Okay, and then we stopped by realizing that okay, phi n is less than f is less than psi n. And there exist measurable functions g and h. Such that phi n converges to g from below, and psi n converges to h from above. And then because psi n is always below f, psi n is always above f, and phi n is always below f, we got this inequality between g, f, and h. G is less than f is less than h. Okay, and that's where we left off last time. So okay, so now remember this subdivision of the interval came from the definition of the Riemann integral. And these simple functions phi n and psi n are something that comes from the theory of Lebesgue integrals. And in particular, if we write down these lower and upper Riemann sums again, then using these definitions of phi n and psi n, the lower Riemann sum is nothing but the Lebesgue integral of phi n. Remember my notation from last time. I write this L in brackets when I mean the Lebesgue integral, and I write a capital R in brackets when I mean the Riemann integral. So this lower Riemann sum is just the integral of this simple function phi n. And similarly for the upper Riemann sum, okay, and now because of these convergences of phi n and psi n, using the monotonicity of the Lebesgue integral, the phi integral is bounded above by the integral of g, and the psi n integral is bounded below by the integral of h. Okay, and we know that h is larger than g, so h minus g is a non-negative measurable function. So we can apply Fatou's lemma. And from Fatou's lemma we get the following. The Lebesgue integral of h minus g is less than or equal to the limit and to infinity Lebesgue integral of psi n minus phi n. Right, so this is actually a lim-inf that comes from Fatou's lemma, but we'll see in a second that it's actually a limit. Yeah, so this is non-negative, and that's why we can apply Fatou's lemma. And now this right-hand side here can be expressed through these lower and upper Riemann sums, right? So this is limit and to infinity upper Riemann sum minus lower Riemann sum of f. Okay, just because the integral of psi n is this and so on. And now, if you remember from last time, we assumed that f was Riemann integrable. So this difference between the upper and lower Riemann sum goes to 0. We know that from the assumptions. So this is 0. Okay, so this is brilliant because now we know that the integral of h minus g is 0. So we got these limits h and g, and we didn't really know anything about them except that they exist and this inequality. And now the Riemann integrability of f gave us some more information about h and g. And in fact, well, this is a non-negative function. If the integral of a non-negative function is 0, then the function must be 0 almost everywhere. Actually, that was one of the exercises on the problem sheets to show that. So integral is 0, therefore h is equal to g almost everywhere. Oh, but now look at this. We have this inequality that says that f is sandwiched between g and h, that h is equal to g almost everywhere. So this implies that f is equal to h is equal to g almost everywhere. Okay, so now instead of just having these inequalities, they're actually almost the same up to a set of measure 0, f, g, and h. And now this implies that f is Lebesgue measurable. And I think that needs some explanation. So we know that h and g are Lebesgue measurable, right? Because they are limits of simple functions. And now f is equal to h or g almost everywhere. So this doesn't immediately imply that f is measurable, because it's only equal almost everywhere to a measurable function. But we're not talking about some general measure space, but the Lebesgue measure. And we know that the Lebesgue measure is complete. So we can do the following. I mean, you can do this, for example. So if we want to prove that f is measurable, we have to, what we can do is take a Borel set, take the pre-image under f, and that this pre-image has to be Lebesgue measurable. And because f is equal to h almost everywhere, we can do the following. Take any Borel set A, then f inverse of A is, well, it's not quite equal to h inverse of A. We might miss something contained in a null set, and we might get too much, but only something contained in a null set. So the f inverse of A will be h inverse of A, possibly minus a set U, possibly union with a set V, and where U and V are contained in a set of measure 0. Because f is equal to h almost everywhere, so up to a set of measure 0. And now, because the Lebesgue measure is complete, everything contained in a set of measure 0 must be measurable, right? That's what completeness means. So sigma L complete implies U, V, are in sigma L. But now F inverse of A is H inverse of A, which is measurable, because H is measurable, minus something measurable, and then union with something measurable, so the entire thing is measurable. And that's why F is measurable. But this is only true because the Lebesgue measure is complete. I'm going to leave it like this. Was this clear? Or does anyone have any questions before we continue? Okay, so let's continue. Okay, so now we know that F is measurable, and now there's not much missing. We just have to compute, we have to compare the Lebesgue integral and the Riemann integral, but now we have all the gear, everything's on the blackboard, we just have to piece everything together. So by Riemann integrability of F, we know the following. We know that the lower sums converge to the Riemann integral of F, and the same is true for the upper sums. Okay. But now we have the following string of inequalities. The lower sum L of F comma delta n is the same as the Lebesgue integral of phi n, b phi n dx. This is bounded above by the Lebesgue integral of F this is bounded above by the Lebesgue integral of the psi n, and this is the same as the upper Riemann sum of F. Okay, and now look what we have. In the center, we have the Lebesgue integral of F. On the left, we have something that converges to the Riemann integral of F. And on the right, we have something that converges to the Riemann integral of F. So if we take this string of inequalities and let n go to infinity, then we get Riemann integral on the left-hand side less than or equal to Lebesgue integral of F less than or equal to the Riemann integral of F. And now this implies that the Lebesgue and the Riemann integral are equal, right? The Lebesgue integral is sandwiched between the Riemann integral of F. And that's the end of the proof. Okay, any more questions? Yes.
Sorry, I have thought of a question about this bit here with the Borel set.
Yes.
Why do you need to show the inverse of a Borel set is measurable and not?
You
this
could take a
half?
half line as well. It's equivalent because because these half lines generate the Borel sigma algebra. So maybe it makes more sense to take a half line here, just because that was the definition. So we're not using any theorems where we don't have to, because the proof stays the same. So maybe it's better to write A to be to be such a half line. Is that what we, hang on, no, x larger than alpha, right? That's what we had in the definition of measurable functions. Right? And then
F of x.
yeah, so okay. So what we did in the definition was we had an f of x here. So that's not, yeah, okay. So the proof would maybe change a little bit.
This is what I don't understand, is the set depends on F, right? Your A that you need to prove it for depends on F.
Yes.
So how would we know that the inverse, because they agree almost everywhere, like how do we know that the inverse image over H would be?
Think at the moment. I'll tell you after the break. So if we start with the Borel set here, then that's fine. This proof is correct. And if you do it with the half line, maybe you have to do it slightly differently.
How do we know that the inverse, with the Borel set, how do we know that the inverse image of a Borel set through H is measurable?
Because H was assumed to be, because we know that H is measurable.
And I don't see how, and how would that imply that because Borel sets are made of half lines?
Yeah, that was basically, I think we had an exercise on one of the problem sheets that showed basically this, that it's equivalent to take the definition with the half line or to look at pre-images of Borel sets.
Okay.
But it would be nicer to show it directly from the definition. Yeah, I'll sit down in the break and try to sort my head out. But yeah, like this, I mean, it's also fine. So this, what time is it? Yeah, I suggest we do one of the exercises now on the blackboard. Then we take a 10-minute break, and then I'll come back to this. And if not, I'll write you an email and explain that. So yeah, this way the proof was easier. So okay, let's just move on with the exercises. So are there any other questions about this proof before we move on to the problem sheets? Looks like no. Okay. So the exercise I wanted to do was part B, exercise 3. Because part B, exercise 3, first, it's just the proof uses many techniques that are often useful to solve exercises, so it's a good practice for you. And second, exercise number 3 is actually the proof of proposition 4.28, which said that if the integral of a non-negative function is 0, then the function is 0 almost everywhere. So that's actually what we used here. So this step is justified by this exercise. And the exercise was to show actually a little more. So the situation was this, given a measure space, x sigma mu, there was a set S in sigma, and assume that that mu of S is 0. Then the following function, f of x is infinity when x is in S and 0 otherwise. Then the task was to show that the integral of f is 0. So basically, if the measure of a set is 0, the function can be as large as it wants on that set. The function can be even infinity and still the integral is 0 if the set has measure 0. Okay, so this was part A, and part B was if g is a non-negative measurable function. Then the following two statements are equivalent. Integral g d mu is 0 if and only if the measure of the set of all x where g of x is positive the measure of that set is 0, right? Yeah. So this part B here, that's what we've used here. If the integral of g is 0, then this set has measure 0, which means g is 0 almost everywhere. Okay, and the exercise was to prove these two things. To prove part A, so part A could be done, for example, with the monotone convergence theorem. For the following reason. So we have this set S with measure 0, and this function f, which is infinite on S, and we want to compute the integral. So one thing that one can always try is to approximate f from below by simple functions. And on the problem sheet there was a comment that said, attention, this function is not a simple function, even though it's constant on a measurable set and constant on another measurable set, because simple functions are not allowed to be infinity. So if we want to use the integral of simple functions, we have to approximate this from below by simple functions. So what we can do is the following. Phi n, let phi n be the following function, n times the characteristic function of S. Then that's a simple function. This has exactly the correct form that we need for simple functions, and now the value of phi n on the set S is finite. And in addition, phi n converges to f pointwise from below, because n goes to infinity. Well, okay, now we have a sequence of measurable functions, non-negative, which is growing, so we can apply the monotone convergence theorem. And the monotone convergence theorem says that okay, so first we can compute the integral of phi n easily, right? The integral of phi n is just n times the measure of s. But n times the measure of s is 0 because the measure of s is 0. And now the monotone convergence theorem says that the integral of phi n converges to the integral of f. Okay, but this sequence was constant 0. So the integral of f is the limit of the sequence, which is 0, 0, 0. So this integral must be 0. And that's part A. Okay. Are there any questions about part A? Okay, simple enough. So that's again one nice application of the monotone convergence theorem, I think. Because in this statement, there's no sequence, there's no, a priori, there's no reason to consider limit theorems for sequences. But then how do you prove this? And then if you introduce a sequence and then use this theorem, you get the statement for free. So yeah, that shows the power of these convergence theorems. You can use them to get statements that have nothing to do with sequences. So yeah, the monotone convergence theorem and the dominated convergence theorem are really, really powerful. Okay, so this was part A. Part B was to prove this equivalence. So the integral of g is 0 if g is non-negative measurable, if and only if g is 0 almost everywhere. And there were several different solutions for part B. One possibility that uses the hints that were given on the problem sheet is the following. So for the direction from left to right, so assume that the integral is 0, and then we want to prove this. This can be done as follows. Define these sets, En. So let En be the set of all x, where g of x is larger than 1 over n. Then the union of all these sets is this set, right, where g is positive. So this is why these sets will be useful. So define these En and then define the following sequence of functions. The characteristic function of En times 1 over n. Then, by definition of En, phi is always below g, right? Because on En, g is larger than 1 over n. That's why we define phi in this way. So then phi n is less than or equal to g, and we have the following. One over n times the measure of En is the same as the integral of phi n, right? Because phi n is just a simple function, so the integral of phi n is just the measure of En times 1 over n. But now phi n is below g, so the integral of phi n is below the integral of g. But we assumed that the integral of g is 0. Okay, so this holds for every n. So this 1 over n times the measure of En is less than or equal to 0. So the measure of En has to be 0 for every n. Okay, so this is pretty nice. And now we use two facts. First, these sets En are growing, right? Because this condition becomes weaker and weaker as n grows. So these are all nested. And as we said, the union of all the En is precisely the set where G is positive. So now this should ring a bell. This property means that we can use the monotone convergence theorem for sets. And the monotone convergence theorem for sets tells us that the measure of the union of the En can be written as the limit for n to infinity mu of En. Okay, but now we're done, because this right-hand side is 0. Because all the mu of En are 0. Okay, so we started by assuming that the integral of g is 0, and we concluded that the measure of this set is 0, which is just what we were supposed to do. And now we have to prove the other direction. But the other direction is even simpler. So the other direction, okay, we assume that this set has measure 0. But then we can do the following. We can use part A. Choose S to be the set of all x, where g of x is positive. And let f be the function from part A. So f is infinity on this set and 0 otherwise. Then the integral of g is less than the integral of f, because f is infinity whenever g is non-zero. So f is always above g. But we know that the integral of f is 0 from part A. So this follows from part A, and this follows from the fact that g is less than or equal to f. Yeah, and this shows that the integral of g has to be 0, which is what we were supposed to show. And that's the exercise. Okay, are there any questions about this exercise?
Yeah, like not of my own fault, because I need to do my own out-of-date stuff.
Okay, so let's continue. So I thought about this issue again, and I was just confused. So it's I think now that it's really simple. So in the definition of measurability, we call a function f measurable if this set is measurable. X and x are such that f of x is larger than alpha. But by definition, this set is the same as the pre-image of this half line from alpha to infinity. So in the proof that I've given on the blackboard, just replace the Borel set by this half line and everything's fine. So this is I think a clearer version of what I've written over there. So for any alpha, look at this pre-image of a half line. Then, because f is equal to h almost everywhere, there exists a set of measure 0, n, and two subsets of n, u and v, such that this pre-image can be written as h inverse of the half line minus u, possibly union with v, possibly. But now we know n is measurable, Lebesgue measurable. U and v, because n is measurable, u and v are measurable as well, because this measure space is complete. That was the definition of completeness. Any subset of a null set is measurable. And this implies that this measurable set minus this measurable set union with this measurable set is measurable, because it's complements and unions of measurable sets. And then this is the same as the pre-image under f of this half line. So really, yeah, just get rid of the Borel set and write a half line, and then that matches our definition of measurable functions. So this should be clearer than it was before. So is that clear, or are there any more questions? Okay, so yeah, but generally I think it's important to remember, if a function f is equal to a measurable function almost everywhere, that doesn't imply that f is measurable. It's only true if the measure space is complete. That's maybe an important thing to memorize. Okay, so yeah, so sorry I got confused earlier. I should have done this I should have used this half-line definition straight away. Okay, so let's continue. So we've shown that every Riemann integrable function is Lebesgue integrable, and the integrals are the same. And maybe it's worth to stop and think about what this means for a second, because up to now, before we had this theorem, we couldn't really compute Lebesgue integrals, right? We could compute them in some very simple situations when they were 0, or when they were infinity, or when the function was a simple function. But for a function like, I don't know, x squared, we didn't really know how to compute the Lebesgue integral. Now we know. Now we know that it's equal to the Riemann integral, and we can use every theorem from the theory of Riemann integrals to compute this integral. In particular, we have the fundamental theorem of calculus to compute Lebesgue integrals now, because they are equal to Riemann integrals if the function happens to be Riemann integrable. So this is actually really useful, and now we can compute Lebesgue integrals of many functions. So that was just something I wanted to stress. And the next theorem, again, this is proved in the lecture notes, and I'm not going to prove it on the blackboard, because I think it doesn't give much insight. So I'm just going to state it. I think the proof doesn't give much insight, so I'm just going to state it. And if you're interested, look at the lecture notes. So let f be a function on an interval on the real line, and assume that f is bounded. Then f is Riemann integrable if and only if f is continuous almost everywhere. So this is, I mean, the statement of this theorem is really nice, because it gives an exact characterization, right? This goes in both directions of Riemann integrability in terms of the Lebesgue measure. So note that on the right-hand side, this notion almost everywhere, that depends on the measure, right? So this right-hand side is something that's connected to the Lebesgue measure. And on the left-hand side, we just have Riemann integrability. So really, yeah, so this gives another connection between the two theories. F is Riemann integrable if and only if it's continuous almost everywhere with respect to the Lebesgue measure. And as I said, the proof is done in the lecture notes. Okay, and then there are two remarks that I want to make. About this connection between Riemann integrals and Lebesgue integrals. The first one is about this continuity almost everywhere. Because I think it's easy to misunderstand what this means. And in particular, f being continuous almost everywhere is not the same as saying that there exists a continuous function such that f is equal to g almost everywhere. So I think it's important to realize that these are very different things. And one example that shows this is the following. Just take the easiest discontinuous function that you can imagine, just constant, and then a step somewhere, and then constant again. So, question to you. Is this function continuous almost everywhere with respect to the Lebesgue measure? Yes or no? I've seen several nods. Yeah, so those who nodded are correct. So this function, well, what does it mean to be continuous almost everywhere? It means the set of points where it's discontinuous is a set of measure 0, right? Well, the set of points where this function is discontinuous is just one point. And the Lebesgue measure of 1 point is 0. So indeed this function is continuous almost everywhere. But it's pretty clear that there exists no continuous function such that f is equal to this continuous function almost everywhere, right? Because every continuous function would have to be at least close to it would have to have this value almost everywhere, and then it has to somehow transition from this value to that value. But if a continuous function does that, then there's always going to be some open set where f is not equal to g. And open sets have positive measure. So for this function, there exists no continuous function such that f is equal to g almost everywhere. So just keep this counterexample in mind, so that, yeah, this will always remind you that these two things are not the same. Okay, and the second remark is the following. Okay, so in the theory of Riemann integrals, there was a notion of Riemann integrability, which we've seen, which means that these upper and lower sums, the difference of these go to 0 and so on. And that's true for functions defined on a compact interval. So on such functions, this definition works. But then there was also the notion of the improper Riemann integral, and functions being improperly Riemann integrable. And that was for functions, for example, that look like this, so that have a singularity somewhere. And then, you couldn't use the definition of Riemann integrals straight away if you wanted to integrate this from 0 to 1. And then what you can do is to take an epsilon, compute the Riemann integral on the interval from epsilon to 1, because on this interval the function is nice and bounded, and then in the end let epsilon go to 0. And that was called the improper Riemann integral. And that's just a different thing from the Riemann integral. It's not the same. So yeah, one situation was when the function has a singularity somewhere, then you do this epsilon, let it go to 0 in the end. And the other case of improper Riemann integrals were integrals that go, for example, from 0 to infinity. There what you would do is to integrate from 0 to some n, and then send n to infinity in the end. And now the remark is that there exist functions which are improperly Riemann integrable, but not Lebesgue integrable. So this is also important to remember. The previous, the theorem before this one said if the function is Riemann integrable, then it's always Lebesgue integrable. But if it's only improperly Riemann integrable, then it's not necessarily Lebesgue integrable. And I think on the current problem sheet, there's one exercise where you're supposed to give a counterexample that shows exactly this. So you can find a function which is improperly Riemann integrable. So this limit where epsilon goes to 0 would exist, but which is not Lebesgue integrable. And yeah, I'm going to say more about this when we discuss the exercises. Then we can discuss this counterexample. For now, I'll just give this remark. Are there any more questions about Lebesgue integrals and Riemann integrals and any of this? Because this concludes the section about the Lebesgue integral. And now we're going to start an entirely new section about spaces of integrable functions. And the first subsection is about integral inequalities. These inequalities that we're going to show in this section are really, really useful in practice. We might see one of them today already. Really, every inequality we're going to show in this section, if, for example, you want to study differential equations, you're going to use them on a daily basis. I've used these inequalities in my PhD like every day. But that's all going to come. So, as always, at the beginning of a section, we start with a bunch of definitions. First definition is the following. So start with a measurable space, X, sigma mu, measure space, sorry. Let f be a measurable function. Then we define the following two things. The first one is called the essential supremum. S sub over S x of f, which is defined as the infimum of the set of our psi such that f is less than psi almost everywhere. And this is called the essential supremum of f. So the idea is this thing here is like a supremum, but only it takes care of the fact that we're only interested in properties that hold almost everywhere. So you take upper bounds for f that hold almost everywhere, and then you take the smallest upper bound that holds almost everywhere. So really it's like a supremum, but with this additional almost everywhere property. And then analogously we define the essential infimum to be the supremum of psi in R bar such that f is greater or equal to psi almost everywhere. And if both the essential infimum and the essential supremum are bounded, are finite, then we call f essentially bounded. Okay, so that's definition 5.1. And these essential supremum and essential infimum have several nice properties. And you're going to prove them in the homework assignments. So the first one is if f is less than g almost everywhere, then then the essential supremum of f is less than the essential supremum of g, and the same for the essential infimum. And the second part of the remark is that the essential infimum of f is a lower bound almost everywhere for f, and the essential supremum is an upper bound almost everywhere. So essentially the second point means that this infimum and this supremum are actually attained. So these S sub and S inf are still upper and lower bounds almost everywhere for f. And the proof will be homework. Okay. So we can do one short example. To see what this definition means. So for example, we can look at the function, the characteristic function of the rational numbers on the measure space R, sigma L, Lebesgue measure M. So, yeah, maybe I can pose this to you. So, what's the essential supremum of this function, and what's the essential infimum of this function? So, okay, maybe let's start with the essential infimum. What's the essential infimum of this function?
Zero.
Yeah, that's right. Why?
Because it's the infimum, and then the set that it is 0 on is not a null set.
Yeah, that sounds kind of right, but try to use this definition. So,
Okay.
start with the lower bound that holds almost everywhere, and then why is 0 the supremum of that?
Well, if something is larger than 0, then it would not be a lower bound almost everywhere, because the set where it's equal to 0 has non-zero measure.
That's correct. So, okay, yeah, let's start with the essential infimum. So the essential infimum of f, as you rightly said, is 0, because okay, one way of arguing is that every xi less than or equal to 0 is a lower bound for f, right? Because f is just either 0 or 1. So every number that's less than or equal to 0 is a lower bound for f. So this shows that ds actually this x is in this case. So the essential infimum of f has to be larger or equal to 0, right? Because every number that's less than or equal to 0 is a lower bound, so the sup of those must be larger or equal to 0. But then okay, so this these two lines here show that if we take xi, which is less than or equal to 0, and we move it up, we can go until 0, and the essential infimum must be larger than or equal to 0. But now if we take our xi and move it up a little bit further, so it's strictly positive, then the set where f of x is less than or equal to xi suddenly contains the irrational numbers, and that's a set of positive measure. So as soon as xi is strictly positive, it's not a lower bound almost everywhere anymore, because the set where the lower bound is violated has positive measure. So from this line, it follows that m of x are such that f of x is less than xi is actually infinity, right? It's the same as the whole real line. Okay, so this shows if we move xi up from the negative numbers, we can't pass 0. So the largest xi that we're allowed to take is actually 0. So the essential infimum is 0. So that's the essential infimum. And now the essential supremum. What's the essential supremum of f?
always 0?
Yes, that's right. Why?
Because rational numbers, the set of rational numbers is a measurable set with measure 0, so
yes, that's right. So try to argue as we did before with take an upper bound xi and then
xi is greater or equal than 0 is the upper bound.
okay, so for every non-negative xi we have
I would say that f is less or equal than 0 almost everywhere, because the set where f is not less or equal than 0 is only the set of rational numbers that has measures.
yes, that's right. So well, I took psi, so I'll write f the set of x such that f of x is less than or equal to psi is contained in the rational numbers for every non-negative xi, right? No, that's only for every positive xi, sorry, right? Because if xi is 0, then you get the real line. But that's okay. So for every strictly positive xi, the set. Am I doing this right? No, I'm not doing this. It's exactly the wrong way around, right? This is it's this way around, right? F is 0 here, and it's 1 on the rational numbers. So as long as xi is non-negative, the set where f of x is less than or equal to xi contains at least the irrational numbers. So this means that this means that f is less than or equal to xi almost everywhere, because the complement of this set has 0 measure, because the complement of this set is contained in the rational numbers. So this bound is satisfied for every non-negative psi. So this means that because the essential supremum is the infimum of such bounds, that this is less than or equal to 0. Because this holds for every psi which is non-negative. Okay, but now we know that the essential infimum is 0 and that the essential supremum is less than or equal to the essential infimum. And we have this inequality. So we can already conclude that the essential supremum has to be 0. Let me call this star. Then this equation star implies that S sup of f is 0. Okay, so for the characteristic function of the rational numbers, the essential supremum and the essential infimum are both 0. And I hope this showed a little bit how to work with these essential suprema and infima. You take upper bounds or lower bounds which hold almost everywhere, and then you see how far you can move them up or move them down without losing this almost everywhere bound. Okay, now we're going to use these essential infima and suprema to define something new. So let X sigma mu be a measure space and let P be a positive number between 1 and infinity. Then we define the set LP of X, sigma, and mu to be the set of our measurable functions such that the integral of the absolute value of f to the power p is finite. Okay, so LP means I can take it to the power p and the integral is finite. And then we define this is called the P norm to be integral, well, absolute value of f to the power p d mu, and then the entire thing to the power 1 over p. And then we define another set that we call L infinity of X sigma mu, and that's defined as the set of our measurable functions which are essentially bounded. Similarly, we define the L infinity norm. To be the essential supremum of the absolute value of f. Okay, so we have a whole bunch of new spaces of measurable functions, and we define these norms on them. And in the sequel, we're going to study these spaces and try to turn them into reasonable vector spaces that one can work with and just discover properties of these spaces. One more thing that belongs to this definition: if x sigma mu happens to be Rn together with the Lebesgue measurable sets and the Lebesgue measure, then we just write LP of Rn So when we use the Lebesgue measure, we omit sigma L and mu. We just write LP of Rn, and then it's implicit that we mean the Lebesgue measure. Again, it turns out that these spaces are really, really useful in practice. For example, if you study differential equations. But before we can use them, we have to do some work. Because we want to turn them into nice vector spaces, especially Banach spaces, on which we can, which we know a lot about. But first, again, we had a new definition with lots of new information. So let's take a step back and look at one example to see what it means for a function to be an LP. So as an example, let's take the Lebesgue measure in one dimension again. And let's look at the following function. F of x is x to the minus 1/2 times the characteristic function of the open interval from 0 to 1. So f looks like this. So it has this singularity from this x to the minus 1/2 at 0, but outside the interval from 0 to 1, it's just 0. And now we can ask ourselves, is this function in L1? Is it in L2? And we can try to prove that. And that's what we're going to do. So, first, this function f is measurable since because if we look at the pre-image of a half line, so take some alpha on the y-axis and look at all the values that are above. Then you always go, okay, it's not always an interval. So then if alpha is positive, then the x for which f of x is larger than alpha is this interval, right? And if alpha is negative, then, oh no, it's true, right? If alpha is negative, then the x for which f of x is larger than alpha is just the entire real line. And then what happens if alpha is in between this space? Then, yeah, it's an interval again. Then then you get this entire interval from 0 to 1. So the pre-image of such a half line that starts at alpha is always an interval. Yes, that's true. And intervals are contained in sigma L, so this function is measurable. That's the first thing we have to check. And then the claim is the following. F is in L1 of R, but F is not in L2 of R. And for the proof, we actually have to use the connection to Riemann integrals in order to compute the integral of f. So you can prove this as follows. So let's focus on the first one. F is in L1. So of course this singularity at zero is a problem. But we can compute the integral as follows. We can take a sequence of functions by taking a value 1 over n and then cutting off the singularity. So we can define Fn to be the characteristic function of the interval from 1 over n to 1 times f. So in this case, if 1 over n is here, then Fn would only be this bit and 0 otherwise. So Fn, all the Fn are nice and bounded. But of course, Fn converges to f pointwise, and it even converges to f from below. And it's even an increasing sequence. That's what I wanted to say, right? Because it's 0 here. If we increase n, then this point 1 over n moves to the left, and sooner or later it'll be positive. And that's all that happens for this sequence. So it's an increasing sequence. So Fn increases and converges to f pointwise. And even better, Fn is Riemann integrable, right? Because on this interval, it's a continuous function, and continuous functions are Riemann integrable. And it's even Riemann integrable